In our general classes as mechanical engineering students, we are so used to learning about how parts are made or analyzing the stresses on parts, but so often we overlook the work-holding devices that make this part fabrication possible. This fixture design project is intended for us as mechanical engineering students to gain exposure to designing and fabricating a work-holding device. The problem we are attempting to solve is creating a fixture that meets all 7 criteria of fixture design and successfully completes 2 operations in the CNC milling of a tool height gauge holder. The 7 criteria are described later on in this video. The project is necessary for our curriculum as mechanical engineers because it opened our eyes to how work-holding devices are created, and without this knowledge, none of the parts we want to fabricate could be made. It also showed us that there is just as much design involved in making the fixtures as there is in making the parts we want to fabricate.
The overview of this project is to design, manufacture, and test a CNC milling fixture which will hold the IME 450 tool height gauge during the CNC milling operations. The fixture elements used were provided by Mighty Byte, the modeling was performed in SolidWorks, HSM Works, and the fabrication was done using the new Haas CNC mill in the Engineering 41 labs on campus. All this work was done in teams of 2. We hope to learn how to properly design a fixture using the 7 rules of fixture fabrication, which include locating, holding, and supporting parts, using a material that does not fail under process stresses, designing the fixture so that the process toolpaths do not interfere with its features, making it ergonomic for the user, and ensuring that the fixture does not damage the part being made. The key design aspect of this fixture project was making sure that the fixture elements withstood the process forces, modeling and assembling the fixture plate in SolidWorks, and creating the tool paths in HSM Works to better visualize the fabrication process. These elements are described later in the video.
There were multiple specifications and requirements for this fixture design. It must be able to mount to the Haas CNC mill table, be indicated parallel to the CNC machine's axes, be capable of producing one finished part per loading cycle, and both qualify and locate part off of the datums. The fixture design is required to withstand the tooling forces with a minimum factor of safety of 2, and the load and unload time must be under 1 minute. The fixture plate started out as a 0.75 by 5.5 by 11 inches MIC 6 tooling plate, and the CNC blank size was 1.25 by 2.5 by 3.55 inches. The design was constrained by the available Mighty Byte and dowel pin sizes available for this design. The fixture clamps are PN number 10205, and we chose the largest Mighty Byte locating rails, which are PN number 33140.
We started the design by using our knowledge and reasoning from previous fixtures. The locating rails were chosen because they were the biggest available, which would give us the best safety factor. The dowel pins are located on the right side of the CNC operation spaces so that it pushes back when the cutter applies force to the part clockwise. An indicating band was chosen for alignment purposes at the back of the part. Reliefs were between the locating rails and clamps. The bottom of the part was chosen as datum A since that is the primary locating surface on the bottom where it touches the CNC mill. Datum B is horizontally at the middle of the part where the T-nuts will go. This is the secondary surface for locating. The third datum, datum C, is located vertically at the middle of the part. This is so that the clamping and locating components can all be dimensioned from the middle of the part. The final datum is datum D on the side of the locating rail pocket that faces towards the operation space. This is because the parts are cut based on that dimension, so it is critical to the end result. Using the tangential cutting force equations, the tangential force for tool 21 is 2.553 pounds force, and the tangential force for tool 22 is 54.911 pounds force. This gives a safety factor of over 2.0, which meets the requirement. We then used FEA and SolidWorks to ensure that our part would not deform based on unknown loads. Both the von Mises stress and displacements were both relatively small and not a concern.
We used design for manufacturing techniques in this fixture design by keeping the fixture almost completely symmetrical, using the same locating rails on each side and having clear spaces for each component. This prevents the locating and clamping components from being installed in the wrong location. For the methods, we used HSM Works to model the tool paths to ensure that the design was good before we machined it. When putting the fixture blank in the vise, we estimated the distance on the sides of the vise where the blank was sticking out to get it approximately centered. The probe was then used on the Haas CNC machine to locate the fixture blank in the vise before machining it on the CNC machine. We watched the distance to go to make sure that we did not cut into the part and frequently stopped the cutter and turned off coolant before a cut to make sure it was all lined up. For testing, we put the SOLIDWORKS files of the CNC operations into the assembly and associated the tool paths. A stock simulation was ran to make sure the tool paths did not interfere with the fixture. We were not able to get the physical testing done, but we reviewed the SOLIDWORKS models.
And although we did not get to test our fixture by completing the two-part operations, we were able to fabricate and assemble the fixture plate with the Mighty Bite components. The Mighty Bite components fit into the machined pockets, with the exception of the two 4-inch rails. This will be described later in the video. Although the two-part operations were not completed, the fixture was still set up in the CNC mill as if it was going to have completed the machining. This was done for our learning purposes. We used a probe to measure the variation in the Y direction to ensure the fixture plate sat perfectly along the X-axis in the Haas CNC mill. This was good practice in setting up the probe, finessing the handle jog mode, and gave insight into how important it is that the fixture is not askew in the CNC mill.
After the fixture plate was machined, we found that the rail pockets were just slightly too short to fit the rails. It took 2 more tries of adding in relief pockets and machining a slot to connect the 2 pockets for the rails to fit. This was an important lesson in learning to design the fixture. Creating the tool paths were also a source of error for us in this project. We realized that we used the incorrect tool paths to machine the rail pocket, so the corner radii were too large and the part pocket chamfers were too deep, which required some manual deburring.
Based on the 7 criteria for making a fixture, we think our fixture design is great. I think we could have improved our design by using less Mighty Bite parts or making use of existing parts and reorienting the part stocking fixture. We emphasized creating a robust fixture that would withstand the process forces instead of using the space as efficiently as possible. Our problems arose in the fabrication, which were based on the tool paths, tool selections, and making changes in the model. These are all problems that could be avoided, but we learn from our mistakes and will remember those in our future design projects. The fixture we made is designed to just perform this two-part operations and nothing else, so it will not be able to be used for any other projects. Thank you for watching.
Thanks for watching. Have a great summer.